Nano World.
What is nanotechnology and how does it work? Nanoparticles are incredibly tiny, so small that 100,000 of them would fit on a single human hair.
How to view nanomaterials. Scientists use special types of microscope to view nanomaterials. First is electron microscope. German engineers Ernst Risk and Max Knoll built the first electron microscope during the 1930s. This microscope utilizes a particle beam of electrons to light up a specimen and develop a well-magnified image. This type produces higher and better resolution than older microscope because they can magnify objects up to 1,000,000 times. Scanning electron microscope and transmission electron microscope are two general types of electron microscope. Second is atomic force microscope. It is developed by Gerd Big, Calvin Quer, and Christoph Gerber in 1986. It makes use of a mechanical probe that gathers information from the surface of a material. The last type is the scanning tunneling microscope. This type of microscope enables scientists to view and manipulate nanoscale particles, atoms, and small molecules. Another trivia, in 1986, Gerd Binnig and Heinrich Rohrer won the Nobel Prize in Physics because of this invention. And that is how we look on nanomaterials. This is Sharmika Darashan reporting on how to view the nanomaterials.
The nano manufacturing. Nano manufacturing refers to the production of materials and devices at the nanoscale level. It involves the fabrication of miniaturized objects or devices under eventual industrial production. Nano manufacturing can be done through both top-down and bottom-up approaches. The top-down approach involves manufacturing parts by gradually reducing their size, while the bottom-up approach involves building parts from nanoscaled materials. Nano manufacturing methods include processes such as laser ablation, etching, additive manufacturing, subtractive manufacturing, and replication or mass conservation processes. New approaches to the assembly of nanomaterials based on the principles of top-down and bottom-up fabrication includes, first, deep pen lithography. This method involves using the tip of an atomic force microscope to write on a surface by dipping it into chemical fluid similar to an ink pen on paper. Second, self-assembly. This approach involves components joining together to form an organized structure without external direction. Third, chemical vapor deposition. This process involves chemicals reacting to form pure, high-performance films. Fourth, nano-imprint lithography. This method creates nanoscale features by stamping or printing them onto a surface. Fifth, molecular beam epitaxy. It is a technique for depositing precisely controlled thin films. Sixth, roll-to-roll processing. This high-volume practice involves constructing nanoscale devices on a roll of ultra-thin plastic or metal. Seventh, atomic layer epitaxy. This technique lays down one atom-thick layers on a surface. By utilizing these techniques, nanomaterials can exhibit enhanced properties such as durability, strength, lightness, water repellency, UV or IR resistance, scratch resistance, electrical conductivity, anti-reflectiveness, anti-fogging, antimicrobial properties, and self-cleaning capabilities. These characteristics have led to the development of various nanotechnology-enabled products, including tennis rackets, baseball bats, catalysts for purifying crude oil, and ultra-sensitive detectors for biological and chemical toxins. In the future, advancement in nanotechnology may lead to the development of better and more efficient computers with larger memory storage and faster processing speeds. It is also possible that the entire memory of a computer could be saved on a single tiny chip. Additionally, nanotechnology has the potential to create high-efficiency, low-cost batteries and solar cells. These advancements in nanomaterial assembly and applications hold great promise for various industries and technological advancements. This is Mary Geraldine A. Mama reporting about the nano manufacturing.
According to NNI, nanotechnology involves operating at a very small dimension, and it allows scientists to make use of the exceptional optical, chemical, physical, mechanical, and biological qualities of materials of that small scale. And now we will know more about the distinct features of nanoscale. So first is that scale at which much biology occurs. Various activities of the cells take place at the nanoscale. Indeed, the nanoscale is a critical dimension at which many biological processes occur. Understanding and manipulating biological processes at the nanoscale is essential for advancing fields such as molecular biology, biochemistry, biotechnology. Moreover, the intersection of nanotechnology and biology has led to the development of nanomedicine, where nanoscale materials are employed for diagnostic and therapeutic purposes. In summary, the nanoscale is a fundamental realm in biology, and advancements in nanotechnology continue to provide valuable tools and insights that contribute to our understanding of life processes and the development of innovative biomedical applications. Second, distinct of nanoscale is that scale at which quantum effects dominate properties of materials. The nanoscale is the realm where quantum effects can start to dominate the properties of materials. While quantum effects are always present at the atomic and subatomic levels, they become increasingly significant and observable at the nanoscale due to the increased surface area, confinement of electrons, and quantum confinement effects. Understanding and harnessing these quantum effects at the nanoscale have led to advancement in nanotechnology, enabling the development of novel materials, devices, and technologies with unique and tailored properties. Quantum effects become increasingly pronounced as the size of materials approaches or falls below the characteristic length scales associated with the quantum phenomenon. Particles with dimensions of 1 to 100 nanometers have properties that are significantly discrete from particles of bigger dimensions. Quantum effects direct the behavior and properties of particles in this size scale. The properties of materials are highly dependent on their size. Among the essential properties of nanoscale that change as function of size include chemical reactivity, fluorescence, magnetic permeability, melting point, and electrical conductivity. One example is the nanoscale gold, which is not only the yellow-colored element we are used to seeing, but it can also appear red or purple. Gold's electrons display restricted motion in the nanoscale. Practically, nanoscale gold particles selectively build up in tumors, where they permit both precise imaging and targeted laser destructions of the tumor while avoiding damage on healthy cells. Third feature, nanoscale materials have far larger surface areas than similar masses of large-scale materials. As we increase the surface area per mass of a particular material, a greater amount of the material comes in contact with another material and can affect its reactivity. For example, a cubic centimeter filled with micrometer size cubes has a total surface area of 6 square meters, while a cubic centimeter filled with nanometer size cubes has a total surface area of 6,000 square meters. This is Judy Magallanes reporting the distinct features of nanoscale.
There are 12 different findings for nanotechnology in different countries. First, U.S. National Nanotechnology Initiative, where it is known for being the best known and most funded program, and was established by the NNI and has a budget in 2008 to 2009 amounting 1.4 billion to 1.5 billion. Second, European Commission, that was established in February 8 by European Nanoelectronics Initiative Agency Council. Third, the Japan, which established the Nanotechnology Research Institute under the National Institute for Advanced Industrial Science and Technology. Fourth, Taiwan. They established the Taiwan National Science and Technology Program for Nanoscience and Nanotechnology. Fifth, India. They established the Nanotechnology Research and Education Foundation. 6. China established the National Center for Nanoscience and Technology. 7. Israel. They established the Israel National Nanotechnology Institute. 8. Australia. They established the Australian Office of Nanotechnology. 9. Canada. They established the National Institute for Nanotechnology. 10. South Korea. They established the Korean National Nanotechnology Initiative. 11. Thailand. They established the National Nanotechnology Center. 12. Malaysia. They established the National Malaysia Nanotechnology Initiatives. There are also possible applications for nanotechnology in the Philippines. First, ICT and semiconductors. Second, health and medicine. Third, energy. Fourth, food and agriculture. And fifth, environment. Nanotech Roadmap for the Philippines that is funded by the PCAD-TRD DOST. These are the first, ICT and semiconductors. Second, health and medicine. Third, in energy. Fourth, environment. 5. Agriculture and food. 6. Health and environmental risk. 7. Nanometrology. And lastly, 8. Education and public awareness. This is Joanna Kate Macadini reporting about the government funding for nanotechnology in different countries. Thank you.
Benefits and concerns of using nanotechnology. Nanotechnology offers significant advancements in various sectors. However, concerns must be addressed before utilizing and promoting materials derived from these technology. First, nanotechnology is not a single technology. It may become pervasive. Nanotechnology is not a single technology because it is a multifaceted field involving nanometer scale matter manipulation and the development of new technologies, which is prevalent in various aspects of daily life. Second, nanotechnology seeks to develop new materials with specific properties. Nanotechnology focuses on developing new materials by manipulating matter at the atomic and molecular level, enabling the creation of unique structures and properties not found in nature. Third, nanotechnology may introduce new efficiencies and paradigms which may make some natural resources and current practices uncompetitive or obsolete. Nanotechnology's efficiency-enhancing capabilities may soon render it obsolete, leading to the replacement of it with a new technology. Fourth, it may be complicated to detect its presence unless one has the specialist tools of nanotechnology. Scientists are using special microscopes like electron, atomic force, and scanning tunneling microscopes to view nanomaterials. With the rise of nanotechnology, there are benefits and of course, there's also concerns regarding its application in different areas. Environment. The benefits of nanotechnology include improved environmental detection and removal of contaminants, development of benign industrial processes, but also raise concerns about high reactivity, toxicity, and lack of nanospecific APA regulation. Health. The improvement of medicine and health can address low healthcare quality, but it also raises concerns about cell membrane cross-translocation and FDA approval for cosmetics and supplements, preventing safe and effective ingredients use. Economy. Nanotechnology enhances economy by producing better products and creating new jobs, contributing to high GDP. However, concerns include wealth redistribution, clean-up costs, healthcare costs, and accessibility to all income levels. There's no denying that advancements brought by nanotechnology has made a great results to different aspects of our lives and to our community. But like all technologies, it may have unintended effects that can adversely impact the environment, both within the human body and within the natural ecosystem. This is Mavel Madrid reporting the benefits and concerns of using nanotechnology.